right, so double angle for cosine. Cosine 2x. We had 3 different formulas. Somebody give me one of them. What's one of the formulas for cosine of 2x? 2 cosine squared x minus 1. That was one of them. All right, I'm just going to do a little bit of rearranging of this formula. First thing I'm going to do is I'm going to add 1 to both sides. So I'm going to write 1 plus cosine of 2x equals 2 cosine squared x. And then I'm going to divide both sides by 2. 1 plus cosine of 2x over 2 equals cosine squared x. Written this way, that's called one of the power reduction formula. Why would you call that a power reduction formula? I'm taking my exponent, instead of writing a cosine squared, I'm getting rid of the exponent and I'm writing things that only have a cosine in it. So my power on this side is a power 2, my power on that side is a power 1. That's a power reduction. Now, unfortunately, in this class, there aren't any really useful reasons to have the power reduction formula, but this is a very important formula in calculus. When you get to, again, doing something called integrals involving trig functions, you use this power reduction formula a lot. So I'm just going to throw it out there. It doesn't show up in your book. What they do in your book next is they take this formula and they take square root of both sides. So what happens on the right-hand side? If I take square root, what's the square root of cosine squared? Just cosine. So I'm going to write cosine x equals, over here I'm going to take square root, and we remember that when we do square root on both sides, there's always a positive and a negative. So I'm going to write that as cosine x equals plus or minus the square root of 1 plus cosine 2x, all divided by 2. And then I'm going to make a small little change. Wherever I see an x, I'm not going to write x anymore. I'm going to write theta over 2. So this formula is typically written as cosine of theta over 2 equals plus or minus the square root of 1 plus cosine. What happens when I take theta over 2 and I plug it in there? I get cosine of just theta divided by 2. And this is called half angle identity. Why would you call that one a half angle identity? Well, on the left-hand side, I have theta over 2. That's half of an angle. All right, you could go through the exact same thing. I'm not going to work it all out. If I started with cosine of 2x equals 1 minus 2 sine squared x, I could go through the same things, and I would end up with sine squared x is 1 minus cosine of 2x over 2. And again, that would be another power reduction formula. Just trust me that you subtract the 1, you divide by the negative 2, that's what you get. And then I'm going to do the same trick. I'm going to do square roots, and I'm going to plug in x equals theta over 2. And we end up with sine of theta over 2 is plus or minus the square root of 1 minus cosine theta over 2. And this is the other half angle identity. Okay, so those are really the 2 new formulas in this section. The 2 new formulas are the half angle identities. Like I said, the power reduction formulas, they're very important in Calc 1 and Calc 2, but don't really show up in this class. Okay, so I might ask you, what's the cosine of pi over 12? What would you do? Can I write pi over 12 using any of the famous angles that I know? What are the famous angles that I know? 0. What are the other famous angles?
15, 30, 45, 60, 90.
I don't know much about 15 degrees. But I do know a lot about pi over 6 and pi over 4 and pi over 3 and pi over 2, which happen to be 30, 45, 60, and 90 degrees. Can I write pi over 12 using any of those angles? How about cosine of pi over 6 divided by 2? Is pi over 6 divided by 2 the same as pi over 12? Yes, I think so. How come? Or you take pi over 6 and divide it by a nice little low number like 2? You think of 2 as being 2 over 1, you flip and multiply, you get 12. So, according to my half angle identity, cosine of pi over 12 is the same as cosine of pi over 6 over 2. Cosine of pi over 6 over 2 is plus or minus 1 plus cosine theta over 2. Should I use the plus or should I use the minus? Plus, why? 50-50 chance, and I took a guess. Because our angle pi over 12 is in quadrant 1. In quadrant 1, cosine is positive. So in this case, I should use the positive square root. So this is the square root of 1 plus the cosine of pi over 6 over 2. So that's the square root of 1 plus. What's the cosine of pi over 6? Root 3 over 3 or root 3 over 2? Root 3 over 2 is what you meant? That's good, because I think that one's right. Over 2. Now, inside my square root here, I'm going to multiply top and bottom by 2. This is typically written as square root of 2 plus square root of 3 over 4, which could then be written as square root of 2 plus square root of 3, all divided by 2, because down on bottom the square root of 4 is 2. Questions on that? So on that worksheet the other day, somebody asked me, how did I know the cosine of pi over 2 was that ugly number? What I had done to find the cosine of pi over 12 is I had used the half angle identity and got that answer. Questions on that? Okay, so similar idea. What if I asked you for, I think you'll find this one easier. People tend to like degrees better. What if I asked you for sine of 15 degrees? Can you write 15 degrees in terms of any of the famous angles that you know? You could write it as 45 minus 30. That's true. How else could you write it? 30 over 2. That's the one I want to use for this one. Why do I want to use sine of 30 over 2? Because right now we're talking about the half angle identity, so I want to use the half angle identity. Let's do it as sine of 45 minus 30 also and see if we get the same answer. That'll be interesting. So we'll do this problem twice. Oops, that's not what I want. Sine of 15 degrees is sine of 45 minus 30. So we'll do this problem two different ways and see if we get the same answer. Okay, so sine of 30 degrees over 2. Again, I look at my formula sheet. Sine of 30 over 2 plus or minus square root of 1 minus cosine 30 over 2. Again, do I use the positive square root or the negative square root? Positive because 15 degrees is in quadrant 1. So it's positive square root 1 minus cosine of 30 degrees over 2. That's the square root of 1 minus. What's the cosine of 30 degrees?
Square root of 3 over 2.
Square root of 3 over 2. So she's trying to mess with me, give me the wrong answer. Square root of 3 over 2, all over 2. Again, if I wanted to, I could multiply top and bottom by 2 and write this as square root of 2 plus square root of 3 over 4. Minus. Thank you. 2 minus square root of 3 over 4. And then again, down on the bottom, square root of 4 is a nice number. Square root of 4 happens to be 2. So I could write this as square root of, oops, that's not what I wanted. Square root of 2 minus the square root of 3 all over 2. All right, now let's do it this way. Sine of 15 degrees, I could write that as sine of 45 degrees minus 30 degrees and use the difference formula and see if I get the same answer. How does this work? How do you take sine of something minus something? You go to the formula sheet, all right? Let's see, sine of something minus something. You do sine and then cosine. And then you subtract and you switch them. You do cosine and then sine. Okay, so according to that formula, this is going to be sine 45 degrees cosine 30 degrees minus, I flip them, cosine 45 degrees sine 30 degrees. And then I simplify them all down. Sine of 45 degrees happens to be root 2 over 2. And the cosine of 30 degrees is still square root of 3 over 2. Minus cosine of 45 degrees, root 2 over 2. And sine of 30 degrees, 1/2. So this is square root of 6 over 4 minus square root of 2 over 4. That's square root of 6 minus square root of 2 all over 4. Did I get the same answer? Well, they certainly don't look the same. Are they the same? Put them in my calculator and find out? All right. Let's see. Square root of 6 minus square root of 2 divided by 4. So there's that one, 0.2588. Now let's try this one. Square root of 2 minus square root of 3 all divided by 2. Does it look like I got the same answer? It certainly does. So that's mildly interesting, I suppose, that you can find the sine of 15 degrees in two different ways. You get two answers that look pretty different, but it turns out they really are the same.
Do you need to put that second one or not?
That's an interesting question. His question is, can you simplify some way to make this one look like that one. Maybe. Any ideas how you might do that? I'm not sure how to do it right off the top of my head. What I would try is I might try multiplying this one top and bottom by 2 plus square root of 3 to do a process like rationalizing to get rid of this double square root and then see if it simplifies and see if I can break it down. But I don't know how to do it right off the top of my head. That would be my first guess as to what to do. Other questions? All right, so on, what's today? Today's Monday. On Wednesday, we'll do some more problems involving half-angle identity, double-angle identity, so on and so forth.